Hello everyone, welcome to NPTEL online course on electric vehicles. In our previous interaction, we have started a topic vehicle dynamics and we have covered few topics under the vehicle dynamics such as introduction and tractive effort. Let us see some simulations with respect to the topic of tractive effort in today's interaction. So, we have seen that the total effort that is required to move the vehicle is a sum of various forces such as force due to rolling resistance, force due to gradient or slope, force due to aerodynamic drag, and force that is required such as linear acceleration and angular acceleration if you want to provide change in speed when the vehicle is moving. So, if we substitute the formulas of each of these forces, we get this equation. So, force due to tractive effort is FRR, which is mu RR mg cos theta, force due to gradient is mg sin theta, force due to aerodynamic drag is half rho CD A and square of the addition of vehicle velocity and air velocity, and also we have acceleration forces due to linear movement and angular moment. So, we know that the aerodynamic drag force is a function of square of vehicle velocity. So, if you want to see the variation in aerodynamic drag power with respect to vehicle velocity and also with respect to wind velocity, it will be good idea to plot the aerodynamic power with respect to different vehicle speeds for known value of drag coefficient, frontal area and air density. So, let us assume that we have a drag coefficient of 0.26, frontal area of 2.2 meter square and air density of 1.2 kg per meter cube. So, if we see the power due to aerodynamic drag at different vehicle speeds, let us say we will see the variation from 0 km per hour to 100 km per hour. We will see a graph which is this graph. So, we can see that the power is a q function of speed. So, therefore, the power required at very high speed is significantly high. So, let us say at 50 km per hour the power required is around 1 kilowatt, while when the vehicle is operating at 100 km per hour the requirement of power is 8 kilowatt. So, just by doubling the speed from 50 km per hour to 100 km per hour, the power required changes from 1 kilowatt to almost 8 kilowatt. So, this is a huge variation. Secondly, let us see that in addition to vehicle velocity, if there is a strong wind of let us say 10 km per hour opposing the vehicle movement, then what will happen? So, this second curve shows that effect. So, if the wind velocity of 10 km per hour is opposing the vehicle movement, you need extra power of around 2 kilowatt at 100 km per hour. Now, let us see the effect of variation of aerodynamic drag coefficient, which is CD, on the aerodynamic drag power. So, let us see that the previous case example, but with two values of CD. So, we have CD of 0.26 and CD of 0.4. The area is similar 2.2 meter square and rho of 1.25 kilometer per meter cube. So, if we take this example, we can see that if we increase the CD from 0.26 to 0.4, the amount of power needed increases from 8 kilowatt which we need when the CD is 0.26 to around 12 kilowatt when we are operating with a CD of 0.4. So, we need to support extra 4 kilowatt power if we are running at 100 kilometer per hour. So, you can see that the effect of this coefficient is quite high, and there should be every effort to reduce the drag coefficient in electric vehicles, because this amount of power requirement can put significant stress on battery energy capacity. Now, let us see all the forces and their variation together. So, let us see the gradient force, aerodynamic force and rolling resistance force, and the addition of these forces, which is a tractive effort, together in a same graph. So, we want to see the effect of this vehicle velocity on these forces and the power variation. Again, we will take the example which we have taken earlier, that is CD of 0.26, A of 2.2, rho of 1.25, and let us assume a flat road where the theta is 0. So, when the theta is 0, we know that there is no power required in terms of gradient force. So, it is 0, because mg sin theta and sin theta is 0. And this is the variation of force and the corresponding power required to support rolling resistance force. So, say dominantly a straight line. So, this is a weak function of speed, as we have seen. And when we talk about aerodynamic force, which we have already seen, so it requires around 8 kilowatt at 100 kilometer per hour. So, this is continuing the same graph as we have seen earlier. So, the total tractive effort is somewhere around 10 kilowatt. So, it is a addition of, so PTE is addition of PAD plus P rolling resistance plus P gradient. So, gradient force is 0 here. So, let us see the similar result when we are operating at a theta of 3 degrees. So, let us say the vehicle is moving on a slope of 3 degrees, and when we are operating the vehicle at different speeds. So, in this case, the only variation will be in terms of gradient power. So, gradient power now is extremely high. So, at 100 kilometer per hour, it requires almost 20 kilowatt power. So, if we are driving the vehicle on a slope of 3 degrees, the gradient power itself is so huge, it is around 20 kilowatt. The total tractive effort will be somewhere close to 35 kilowatt. So, you can see the effect of slope. So, moving the vehicle on a slope versus a flat road is enormous. So, this effect will be very high if we are running at high speed on a slope. So, effect increases linearly. So, it also tells us that if you are operating an electric vehicle on a hill or in a slope terrain, it puts a heavy burden on the vehicle battery. So, it is always advised to operate the electric vehicle on a flat road terrains for having a good range. Similarly, let us see the effect of all these forces when you are operating at a theta of minus 3 degrees. It means that we are driving the vehicle down the slope. So, in this case, again similar to the previous case, the gradient power required is around 22 kilowatt at 100 kilometer per hour speed. So, when we see the total tractive effort now, it is negative. So, it increases with the tractive effort up to 70 kilometer per hour, and after that it becomes flat and maybe started decreasing. So, what happens at that higher speed? At higher speeds, the power taken away by aerodynamic drags becomes very significant, and the power what we can regenerate becomes lesser because the aerodynamic power becomes significant at higher speeds. So, these graphs can be plotted using simple simulation files. So, in this course we are using MATLAB as the simulation tool. So, the simulation file used to plot these graphs is elaborated here. So, first generally in a simulation file we have to define the parameters and their values. So, in our case we need to define the rolling friction coefficient which is let us say mu RR, let us say 0.01, drag coefficient of 0.26, area of 2.2 meter square, mass of 1500 kgs, air density of 1.25 kg per meter cube, theta we can define in degrees, vehicle of the wind we can give in kilometer per hour, but if we multiply it by 5 by 18 we convert it to meter per second. Then since we are plotting all the powers and the forces, so these are forces due to all aerodynamic force, rolling resistance, gradient and total tractive power and power. So, we have to define all these variables, and also we have to define arrays because we need to store lot of data. So, against each speed we have to calculate the power and store as a data. So, we have to create arrays, and where the values of this different forces and power will be stored. So, we have to define velocity as well, velocity, forces and powers. Then we can run a for loop, and the loop has to run in number of steps. So, let us say that we are operating at the step of 1 kilometer per hour. So, we are varying the speed from 0 kilometer per hour to 100 kilometer per hour at a step of 1 kilometer per hour. So, for each iteration we will calculate all the forces, the total tractive effort, all the power and the total tractive power for each velocity, and will store the results in the array of 100 values. So, having got the values, we can plot this power versus velocity in either meter per second or kilometer per hour. So, whichever is feasible, and since the power is quite huge we can plot in terms of kilowatt. So, if we divide by 1000 it means the power will be now plotted in kilowatt and speed in kilometer per hour. So, it is a simple exercise. It can be also done in C language, which is easily available to the students. Now, let us go to our next topic, which is dynamic equations. So, we will try to derive dynamic equations which can be used for understanding the dynamics of vehicle for different kind of force input. So, the input is the force what we get from the propulsion or traction unit. So, how the system will behave for different kind of this traction input force is a important analysis parameter. So, this is the typical drivetrain of a electric vehicle. where a electric motor is connected via gears and differential to the wheels via driving axle. So, we use fixed gear generally in an electric vehicle. So, let us assume the gear ratio of the gear is G and its efficiency is eta G. So, let us try to find some basic relationship between different forces and speeds. So, if we assume that the vehicle is moving at a velocity of v meter per second under a tractive effort of FTE, then we can say that the torque on the driving axle, which is T wheel, is equal to Ft into R. So, this is a very simple relationship between force and torque. Similarly, the angular velocity of the driving axle, which we can denote as omega wheel, can also be found out using this relationship. So, omega v is velocity by R. So, in a typical electric vehicle, the gear ratio is normally taken as greater than 1. It will be in the range of 8 to 10 in most of the cases. We can also find the angular velocity of the shaft of the electrical motor using the gear ratio. So, we can say that omega m is G into omega wheel. In a electric vehicle drivetrain, generally the speed of the motor is higher while the speed of the wheel is lower. So, speed is reduced from motoring side to wheel side. We can also find the relationship of torque of the motor shaft with respect to torque on the driving axle. This can be done using power balance equation, which we can write as follows. So, we can say that the power on the electrical machine shaft can be equal to power delivered on the driving axle. But since we are losing some energy in the gears because of this efficiency, so we can also accommodate the losses in the gears by substituting eta g as a dividing factor to the power delivered on the driving axle. So, generally this losses has to be supported by the electrical machine. So, since we know the relation between omega m and omega wheel, we can find the relation between Tm and T wheels as this. So, Tm will be 1 by G eta G into T omega. So, here we can see that the motor torque is lower compared to wheel torque, since it is divided by G and G is greater than 1. So, In our previous interaction, we have discussed about J axle, which is moment of inertia of the driving axle. So, this is the moment of inertia of all the components as seen by the driving axle. So, if we want to accommodate and understand the relation of the moment of inertia of motor shaft in force equation, we may have to find the relation between Jm and Jxl. So, how we can do that? We can do that by using energy balance equation. So, we know that the energy stored in the mechanical shaft of electrical motor is half Jm omega m square, and this has to be equalized to the energy stored in the driving axle, which is half J axle into omega wheels square. But since we have to accommodate the losses in the gears, we have to divide it by eta g. So, here also we know the relation between omega m and omega wheel, and which can be used to find the relation between J axle and J m as so, let us substitute these relationships on the force equation. So, we know the force equation as addition of different forces, and let us now substitute torque of the vehicle axle on the FTE. So, we know FTE is torque on the wheels divided by R, and also the relation of J axle with respect to inertia of the motor. We can also substitute the motor torque in place of axle torque by means of relation we have just seen as this. So, now this equation is in terms of motor torque and inertia of the motor, and the velocity we are still keeping the vehicle velocity. So, using this equation we can find the amount of torque that is required to be delivered from the motor if we want to operate the vehicle at a velocity which is v with all these resistive forces in place. Let us try to redefine this equation in terms of dynamic equation in terms of velocity. So, if we resubstitute the thing and we bring this term which is proportional to dV by dt on one side, and the tractive effort and the subtraction of all the resistive forces on the other side, we can get this equation. dV by dt will be g by r eta g T m minus all the resistive forces, and this will be divided by the equivalent mass on the vehicle axle. Now, when the vehicle is in motion, there can be different types of tractive effort that can be applied from the motor. So, let us start with a scenario where we are applying a constant tractive effort, means the FT is constant. But in a practical scenario, this FT is not constant, and it will be applied in a certain manner depending on the driving cycle of the vehicle. So, this also will be discussed later. So, let us start with the derivation of dynamic equations when we are operating with a constant FTE. So, when we are operating at constant FTE, the Tm will be also constant, and this whole equation can be written in terms of some simple constants. So, dV by dt can be written as minus k1 v square plus k2. So, k2 is all constant terms plus this k1 is a function of this aerodynamic force equivalents. So, this is the equation. So, we can see the values of k1 and k2. So, k2 is basically the constant parameters, and k1 is this aerodynamic forces equivalent. So, if you want to understand the variation of velocity for this constant force input, we need to solve this equation as a function of time. So, for solving this equation, let us assume few things. Let us say assume that k1 is equal to k1 a square and k2 is k2 a square. If you do this substitution, the solution can be easily derived. So, this equation will become this equation. So, k1 and k2 will be substituted by k1a and k2a. So, once this equation is there, we can rewrite this equation in terms of this way. So, this you can rewrite in terms of this way. So, this is separating variables method, and we want to understand the variation of velocity with respect to time. Let us integrate this over 0 to time t. If we do that, we will get a logarithmic equation which is like this, and this can be further solved in terms of exponential terms. Thus, we can remove this logarithmic term like this. So, now it can be further simplified as this equation, and this equation is a can be easily rewritten as v of t as k2a by k1a tan of h k1a k2a into t. So, this is the equation we were looking at. So, this can be further simplified, and we will again resubstitute the value of k1a and k2a in terms of k1 k2. So, k1a is basically root of k1 and k2a is root of k2. So, if we substitute this, we will get this equation. So, this is the equation of velocity variation with respect to time in terms of variable k1 and k2, which are the parameters of the system, considering all kind of opposing forces and accelerating forces. So, what this equation infer at? So, this infers at this the velocity will start from let us say 0 meter per second, and it will move towards a steady state value as the time elapses. So, what is the steady state value of this velocity? The steady state value or the terminal velocity can be found if we find the limit value as time approaches infinity. If we substitute this limit as time tends to infinity, we will get a very simplified expression which is root over k2 by k1. So, terminal velocity is this. So, we can say that this v terminal value is equal to root of k2 by k1. So, which is a very simple expression. So, once this value is known, we can do this simplified substitution, which is root over k 1 into k 2 is now k 1 into V t, because if you resubstitute this in a proper way, you can able to find this expression, and this can be substituted in this expression of V t as this. So, this is V t and this is k 1 V t. So, this is the simplified expression of V t in terms of terminal velocity which the system will finally end to. We can also use this equation to find the distance the system travels in a finite amount of time. So, V t is nothing but d by dt of s t. So, s is basically distance. So, if we integrate this, we can get the expression of s of t. So, s of t is 1 by k 1 logarithmic of cos h k 1 V t. So, this is exponential graph, and let us say we want to understand the starting acceleration. Let us say we want to understand that if we are operating the vehicle and increasing the speed by constant torque input, and we are increasing the speed from 0 meter per second to let us say V f meter per second, and it typically takes a time equal to T f. So, when we are operating and going from 0 to V f speed, the time required is T f. So, what is this T f? So, we know the starting value of speed and the let us say final value of V f, which is lesser than V t. Then what is the time required for achieving that speed? So, that can be simply evaluated by using the expression of V. So, instead of V of t, we will substitute V f, and t will take it on the other side, and it can be just 1 by k 1 k 2 tan h inverse and this expression. So, this is just a reverse expression of the velocity expression. Let us say roughly we want to find the time when the velocity reaches almost 98% of the V t. So, if you want to understand T f for this speed range, then we can simply substitute V f as 0.98, and we all know that root of k 2 by k 1 is V t. So, if we substitute this, we will get a very simplified expression for T f. So, this is a rough value of time we need to achieve 98% of the terminal velocity, which is 2.3 by k 1 into V t. So, these are some simple formulas which can be used to do some performance analysis. So, once the T f is known, we can also find the distance which is transferred or achieved when we are reaching the velocity of V f. So, we just substitute the T f in the expression of distance. We would also like to calculate the instantaneous power that is required to achieve this kind of operation. So, since we are operating at a constant input force of F t, the plot of power will be similar to velocity plot. So, it will be also similar to this. So, we are achieving the velocity V f at time T f. So, let us see the expression of power. So, P tractive effort is a product of F tractive effort into velocity. So, this can be just written. So, this is a constant number and V t is also constant number. So, these constant numbers can be clubbed and we can say that this is nothing but terminal power. So, when the V t is reached, the power required is P of t, and the power required by the shaft of the motor is this power divided by efficiency of the gear. So, we can also find the power that is required when we are operating at velocity V f during time T f by just substituting T s T f here. So, the instantaneous power equation is very important, but for energy calculations we need to find the average power that is required by the vehicle when it is operating from 0 rpm to the required rpm. So, it is always a good idea to calculate the average tractive power that is required. So, average tractive power will be somewhere here. So, it can be evaluated by doing the integration 1 by T f 0 T f in the expression of t with respect to time, and we will get this expression. This is very important expression in terms of energy requirement that we will see. So, in an electric vehicle all the power is coming from battery, and the integration of the power with respect to time is the energy. So, P t is nothing but d by dt of energy, or energy is the integration of the power required. So, if we can understand the P t average, we can just multiply by T f to calculate the delta energy required from the battery. So, that is why this expression is important, and when we want to understand the energy required to be delivered from the motor shaft, we have to just divide it by the efficiency of the gears. So, that is all under dynamic equations. So, here we have covered the derivation of dynamic equations in terms of force and velocity, the expression of distance, power, energy, all this for a constant input effort. So, we have discussed constant input effort. So, we are yet to discuss the dynamic equations when the F t is not constant. So, in our next interaction we will try to simulate these expressions of velocity, distance, power, energy, all these equations for a known system and try to see its effect for different types of vehicle parameters, etc. So, we will do that in our next interaction. So, thank you for listening the lecture.